Our first, no one from the first paper in this session is here right now, so we will go ahead with the second talk, which is going to be given by Jiayi Xian. And the paper that she's going to be talking about is on the facility location problem in online and dynamic models. So just to get a bit of heads up, Jiayi, can you just share the screen?
Yeah, let me.
So Jiayi will be talking for about, I guess, 8-9 minutes, and then that'll leave us time for a quick question or two. And we have a 10-minute slot for each paper, so 10 minutes is a upper bound on how long you can talk. All right, I think we can get started then with Jiayi. Yes, so she's going to be talking about on the facility location problem in online and dynamic models.
Hello everyone, I'm Jiayi Xian, and my topic is on the facility location problem in online and dynamic models. I mainly talk about the online models. It's my honor to speak for my collaborators. So let's get warm up with the problem setting of the offline version of UFL problem. For the offline version, we are given a set of facility F and a set of C of clients, a matrix over F and C. So that just show as this picture. Each client is required to connect to one of facilities. This connection to connect to an open facility. To open a facility, we need to pay facility cost, which is Fi. Then the connection also need to pay a connection cost, which is exactly the distance between the client and the facility. The goal is to open a subset of facility to minimize the overall facility costs and the connection costs. That's for the offline setting. There are actually several results for the offline setting problem. The most relevant algorithm to our problem is the local search algorithm. And the local search actually can give the 3 approximation ratio solution. What is the local search? Local search is when you are given a solution, you're going to apply any so-called local operations if they can reduce the cost of S until no such operation can be found anymore. This includes open the facility I or close the facility I, or swap to facility, which means open a new facility and close an open one. So this a not very complicated proof can give a free approximation. And this can be improved to a 1 plus square root of 2 via scaling. Then let's move on to the online setting. For the online setting, the facility set is given beforehand. Then the clients come one by one at each time step. Then when a client comes, we need to connect it to an open facility or open a new facility to connect it. The first version, the first model that started is the so-called irrevocable model. That means when you make a connection, you cannot change the connection anymore. Even there will be a closer facility open in the future, you're not going to reconnect the client to this closer one. And plus, once the facility is open, it cannot be closed. Even closing a facility definitely reduces the cost. There are some nice results for this setting. The competitive ratio for the online setting is defined to be the competitive ratio, the maximum of the competitive ratio from all the time. The setting we consider is actually the revocable model. That's we want to ask, what if we are allowed to make a few changes to our decision? So the model, the difference between the irrevocable and the revocable is just the decision can be changed. We can close an open facility, we can reconnect a client. So since we introduced the recourse, we need to define it. The recourse is defined to be the number of times we may change. This includes the facility recourse and the client recourse. In most of the time, actually always, the facility recourse is less than the client recourse. We also define the amortized recourse to be the recourse of client, the recourse per client. The goal is to maintain a very good competitive ratio while keep the amortized recourse small. That means we are not going to do too many changes, but we still want to get a very good approximation ratio solution from all the time. Our result is we can have a 1 plus square root of 2 plus small epsilon competitive algorithm that achieve for online facility location with a big O log n amortized client recourse. Here we are going to show the algorithm for the competitive ratio 3 instead to be simplified. The idea is quite natural. When a client comes, we first connect it to a facility. We may connect it to a nearest open facility or may open a new facility to connect it, depending on which one costs less. Then we do local search. So recall that what a local search algorithm can give us is a constant approximation ratio solution. This algorithm has the potential to give us a constant approximation solution. What we need to concern about is the recourse, because we may do a lot of local operation to just reduce the small amounts of cost. Now, to bound the recourse just means we don't want to do too many recourse. We want to skip those operations that contribute too little to reduce the cost. That means we just want to do the local operation that can contribute effectively in reducing the cost. And that's how we come to the definition for efficient local operation. That means we only do local operation only if this operation can reduce the cost by more than 5 per reconnect on average. Then, similar to the classical result, we can prove that when there are no 5 efficient operation can be done, we have the current cost, we denote it as cost as sigma. Sigma is the connection configuration. It's less than some terms of the optimal solution. Then when we carefully set the value of the phi, we can have the right-hand side to be 3 plus epsilon times OPT. OPT is the optimal cost. That means even we skip all the other tiny reduction local operation, we only do the phi efficient local operation, we can still have a 3 approximation ratio solution. That reach our first goal to keep a constant approximation ratio solution. Now let's bound the recourse. To bound the recourse, we need to define the delta t. Delta t is the cost increment due to the arrival of the client, JT. That means the client arrived at time step t. We have a key lemma that is the sum of delta t can be bounded by the optimal solution times a logarithmic factor. This is very important because we have some connection with the delta t and the optimal solution. Since this sum is small, it's bounded by the this right-hand side, and each phi efficient local operation need to reduce the cost by at least 5. So now the recourse can be bounded by this term divided by 5. Roughly speaking, the recourse per client after a few calculation and a small trick, you can get the results big O log t divided by epsilon, and with a logarithmic factor 1 over epsilon prime. So that's our result. Then we consider another setting called the dynamic algorithm. In this setting, we care about the update time instead of recourse. Now, doing a file efficient recalls is not enough. We have to apply random local search because we want to get we want to largely reduce the update time. And we also maintain a heap structure in this algorithm. We can prove that we can maintain an approximation rate factor of 1 plus square root of 2 with total update time of big O n square Pauli log n. The frame of this algorithm is similar to the primer setting. It's because we still have a key lemma, which is similar to the key lemma we just talked about to bound the increment of the total, to bound the sum of the total increment. And then we divide it by the number of times to do the randomized local search. Then we get the update time. That's for this algorithm. Finally, we consider the fully dynamic setting, which means the clients can arrive and depart. And we can prove in this setting for the HSD metric, there's an algorithm that achieves constant approximation factor and BO n log cubic D total update time. The D here is the aspect ratio. Then this theorem actually implies that since we can embed any metric into the HSD with a distortion BO log n, so the first theorem implies the second one, we can achieve a BO log n approximation factor and the similar order total update time. So that's all.
All right, thank you. I think we are just on time, so maybe we will just move on to the next talk. So we swapped the order of the first and second talks, but now I see that Sai Sandeep is here. And so I'm going to invite him to share his screen now. Thank you, GIE. And we will go ahead with the first talk now.
Sorry, who is the next speaker?
Sai Sandeep.
Yeah. Okay, enable screen sharing.
Yeah. So Sai Sandeep is going to be talking about the paper Permutation Strikes Back, the Power of Recourse in Online Metric Matching. Sai, can you?
Yeah. Hi, can you see the screen?
Yeah. Okay, so go ahead.
Yeah, so this work is about online metric matching with recourse. So we'll first start with introducing the problem quickly. In the online metric matching problem, we have a set of servers that are predefined and given to us on a metric space. And we also know the number of servers and n clients arrive one by one. And when a client arrives, we need to match it to one of the servers that are available to us. And as in any other online setting, any server that is used cannot be used again. And the goal is then to minimize the total cost of the matching. So this is in contrast with traditional matching settings, where usually the goal is to maximize the number of edges or something. But here the key difference is that you always get n edges, but you just have to minimize the cost of the matching. And so again, in any our goal is to minimize the competitive ratio, which is the ratio of our cost with respect to the optimal cost. So for example, in the example here, the green edges are the optimal cost, optimal offline cost. That is the optimal matching between all the clients and the servers once they have fully arrived, and our matching, which we do online. And this thing studied on general metrics and also some specific metrics. And on general metrics, the best competitive ratio is 2k minus 1. Here k is the number of servers. And this algorithm, we can prove it to be tight on star metric. There are also works on randomized algorithms where the adversary doesn't know the random bits that we use. And here there's a gap of log k, there's an upper bound of log square k. And the same star example gives a log k lower bound. And so it seems, and one other important case is the line metric. There are also other names for this, is sometimes referred to as key rental problem, this line metric. The same problem, but all the servers are online, like one-dimensional things. And here there is a significant gap between the upper bound and lower bound. So the upper bound is log k and lower bound is 9 plus epsilon. And interestingly, there is a log k lower bound for certain specific type of algorithm. This is an outstanding open problem to resolve the gap. So in this work, we go in a different relaxed version of the problem where we add recurse. So in the original setting, when a client arrives, you cannot change and once you match it to a server, you cannot change the matching. But now we say that we allow it to change it to match it to a different server later when a new client arrives. But of course, the trade-off is between the amount of recourse versus the competitive ratio that you maintain. And here there are two variants, per client versus amortized. That just as the name says, per client recourse is that each client changes its matching at most this many times. Versus amortized recourse is the total number of changes of all the clients is at most t times the number of clients. So our main result is that you can get improved competitive ratios if you allow a modest recourse. So for general metrics, if you allow log k recourse per client, you get a order log k competitive algorithm. So recall that the general metrics, the best ones are 2k minus 1 competitive algorithm with no recourse. But here you can get log k. And for line metrics, we get a order 1 competitive algorithm with the log k recourse. And this is our main result on the line metrics. So in the few minutes left, I'll just give a very quick overview of what's our algorithm. We use this permutation that's the original 2k minus 1 algorithm. And in the permutation, it maintains some offline matching and it uses the offline matching. It updates. So offline matching is at time I is the best matching between the clients so far that have arrived so far and the set of all servers. So we use this as so whenever we update this offline matching and exactly one new server gets added and we match it to that server, this is the permutation algorithm. So our twist on this is that we batch the requests in a clever fashion and then apply this permutation algorithm recursively many times on a specific set of batches. So the original permutation algorithm can be used in batches as well. So our main idea in the general metrics is that we just do the permutation batch algorithm, but on a set of batches that intersect, so that the same client might be there in multiple batches, and that same client might get rematched many times, but the batches are chosen such that you can always get a good competitive ratio. But for line, it's more involved. Line, the matching becomes very you can come up with more properties for matching on the line. So for example, one key property is that a matching on the line between clients and servers is optimal if there are no crossing forward and backward acts. Here by forward, I mean like when a server is to the right of client, and by backward when a server is to the left of client. So this is simply because you can always replace these two with this new matching and the cost has gotten lower. So then our goal is to maintain a matching with no crossing. So you could always do this by just crossing whenever a new arc comes, you just cross everything off. So you'll always maintain an optimal matching like here. But the problem is you could rematch a client many times. So our main idea is that we only cancel one directional arc. So when an arc is forward, we add as it is. But when an arc is backward, we cancel all the forward arcs that it intersects with. So this algorithm as stated is fairly simple, but the analysis becomes slightly tricky because you could have multiple ways to do this when a backward arc comes. So for example, this example here, there are multiple ways to do it. So one way to do it is to first recursively cancel some of the one forward arc and then do it again. So we prove that this algorithm has order 1 competitive ratio by just analyzing the discrepancy, but this algorithm has high recurse. So we modify it slightly by adding a greedy minimizing the number of clients that's in the server idea to minimize the requests as well. So by combining, like these two algorithms have the same compute ratio, and the second algorithm has better requests, so we use the second algorithm. But to analyze the compute ratio, we use the first one, and thus we get the final algorithm with O of 1 request and log k compute ratio. Yeah, that's it. And one interesting question is that our algorithm, actually we don't know if the same algorithm gives O of 1 recurse. So online getting O of 1 compute ratio and O of 1 recurse is I think a very interesting open problem. Yeah, that's about it. And if you have some any questions or something.
All right, let's thank Sai. I think we are still a bit ahead of time, so or over time. So I think we will move on to the next talk in the session. The next talk is going to be given by Baruch Schieber. Baruch, can you share your screen?
Yes, let me see if you get it. Do you see it?
We see your browser. Yeah, okay.
No, you see now my, okay.
Yeah, everything is good.
Okay.
So Baruch is going to be talking about maximizing throughput in FlowShop real-time scheduling. Go ahead, Baruch.
Hi. Good afternoon, good evening, and maybe even good morning for some of you. So I'm going to talk about max throughput in FlowShop real-time scheduling. Most of the 10 minutes I will just devote to explain the problem. Then if there will be no questions, maybe I will give some hints about our techniques. And this is joint work with Lior Benyamin, Jing Li, Kanti Sarpatwar, and Adas Shaknai. And you have all the logos of our affiliations down the slide. So what is the problem that we are looking at? Maybe some of you are not familiar with the scheduling problem, so let me try to define it. So the input to the problem will be a set of n jobs and also a set of machines. The jobs are J1 to Jn, the machines are M1 to MM. And each job will have a release time, a due date, and a wait. So this is why we call it real time, because we have for each job a separate release time and an individual release time and a due date. And each job will be needed to be executed on all the machines in a fixed order. So we can look at it and assume that each job basically consists of M segments, that the segments is to be processed on each of the machines. And there is an order in this segment. So you cannot do the ith segment on the ith machine before you finish the I-1 segment of the same job on machine Mi-1. So you can look at it as like a production line. The production line, you have to go from one station to another, and you cannot do the ith stations before you completed the section I-1. And well, we denote the processing time of the ith segment by PJI. Now, we are assuming that this is non-preemptive. So when we start a segment on a machine, we cannot preempt this segment to schedule another job. And of course, we cannot execute more than one job on a machine at a time. And so remember that we have release time and deadline. So maybe we are unable even to schedule all our jobs within their allotted release times and deadlines, within their what we call time window. So what we would like to do is to find a feasible schedule that will maximize the number of jobs, or the weight of the number of jobs that we can schedule on the machine. So again, we call it the max throughput because we want to maximize the throughput of the system. And the throughput will be the maximum weight of the jobs that we can indeed schedule feasibly. So let me give you an example, just so that we are sure that we understand the problem. So here we have 4 jobs, color-coded, and 2 machines. So you see the segments for each job, the blue job, the green, pink, and yellow, and you see how much they need, how much processing times they need in each one of the machines. we have the machines, and at the bottom, we see the time windows of each of the jobs. So you see that the blue job, for example, the release time is 0, the deadline, the due date is 20, but for the pink job, the release time would be 5 and the due date would be 15. So let us try to, and we have also the weights on the right side. So let's try to schedule these jobs, and let's first do, of course, the naive solution. So we start with the blue job, we put it on machine 1, then we put the second segment on machine 2, and then we go to the green job. So we do some kind of a list scheduling, what we call. So we put it on machine 1, again, it's within their time window, and we put it in machine 2, and now we are stuck. We cannot put neither the pink job nor the orange job or the yellow job. So clearly I'll show you in a minute a better schedule, but let me just mention one more thing about this schedule, because this will come to this term later. This schedule that I show you, it's what we call a no-wait schedule, because it has one more property, which is that you don't wait between segment to segment. So the blue job, immediately after it completed segment on the machine 1, it starts the segment on machine 2, and the same for the green job. I didn't ask for this property, so I may violate it, but I just want to give you the notion of what is called no-wait schedule. Okay, so let's do now the right solution, or the optimal solution. So we start with the green job, and this is still a no-wait schedule for the green job. Now we put the pink job. Note that we have to wait 1 unit because the release time of the pink job is at time 5. So we idle the first machine until time 5. Now we put the pink job, which is not a no-wait anymore, because we put it at the end of the green job. And then we put the yellow job, and lastly we put the blue job, and as you can see, we are able to schedule all the job, and the throughput is maximal because we can achieve all the weights of all these jobs that were given to us. So this is the problem: how to find this type of schedules that will be feasible and will maximize the weight. And there are several application for this problem. Again, this talk is just a teaser for you, either to see the recording of the fuller talk or to read our paper if you are brave enough. So I'm not going to go into the application. Let me just give you one application that was the main driver for our work, and this is autonomous vehicle navigation. So when you are looking at a self-driving machine, the machine needs to understand what's going on around it. So you have a lot of deep learning networks that are running based on information that's coming from the outside. So you can look at this cycle of getting information from the outside using video, let's say, and then a CPU, and then a second segment, which is the GPU processing of the deep learning algorithms. And so you have these two stages, which we call, one of them is the CPU work, the other one is the GPU work. And because this is definitely real time, because when you are seeing an obstacle in front of you, you'd better analyze this obstacle before you hit it. So it's clearly you have a release time, because this is the first time you see the obstacle, and clearly you have a deadline, otherwise you are dead. So this is definitely a deadline. So this is the problem. These are the application. Let me just give you our results. So the nice thing is that no one looked at this version of the problem. So people looked at FlowShop, but not at this specific objective of maximum throughput in the real-time setting. And our first example, our first result is when the number of machines is constant, we can find a pseudo-polynomial algorithm that will yield a 2m+1 approximation, where m is the number of machines. And this is, I say, essentially tight, because there is a lower bound of a related problem, which is omega of m over log m. So let's say that up to logarithmic factor, you have no chance to get any better approximation ratios than linear in the number of machines. So, and this is indeed what we achieved. And for the special case of 2 machines, as a matter of fact, we can achieve a polynomial time algorithm, and this polynomial time algorithm gives approximation ratio of 9. So I'm not going, I don't know how much time I have. I'm not going to describe the algorithms. And then we have 2 special cases that we can get a little better result. One of them is when you have unit weight jobs and the same release time. So unit weight meaning that not each, we just want to maximize the number of jobs that we are doing. And the other one is when we have the same time windows for all jobs. I'm not going to describe this algorithm. I just want to mention a couple of open problems so you can see them on the screen. The one thing that I wanted to mention, and this is, I think that it should be here, and this is why I mentioned the no wait, is can we get an approximation algorithm for the maximum throughput in no wait flow shop model? And why I mentioned no wait, because I really, it's the prior work on no wait flow shop problem is by Gilmore and Gomory, and very a classical paper, as a matter of fact, that shows how to minimize make span in this problem, showing that the TSP problem, traveling salesperson problem, that is defined by this flow shop problem, is solvable in polynomial time. It's a very great, you know, I really recommend this paper. So this is why it will be nice also to find a maximum throughput for this problem. And I see that I'm 13 seconds over my 10 minutes, so I'll stop here.
Right, let's thank Baruch. Maybe we have time for a quick question. I'll ask a quick question. So in the solution that you showed, in the example, it was also a permutation flow shop. Is that also true of your algorithm? And
so this is not always the case. So in the make span problem, this is, I didn't mention prior work, but for 2 machines in the make span problem, it can be shown that permutation, it's always a permutation algorithm. But when you have release time and deadline, this is not the case. It may differ.
Okay. All right. Thank you, Baruch. I think we will move on to the next.
Stop sharing. Let me stop sharing. Okay.
We'll move on to the final talk in the session. That's by June Wong. June, can you share your screen?
Sure. All right.
So June is going to be talking about an extension of Fluker relations with applications to subdeterminant maximization. Go ahead, June.
Hi. So this is a joint work with Nima, my advisor, and we are both at Stanford. So let's first define what is the subdeterminant maximization. Okay. Yeah. So we're given a rectangular matrix A and a parameter K. We want to compute the maximum absolute value among on K by K minors of A. The minor is the determinant of a submatrix. So our main result is that we can get an efficient K to the O of K approximation for this problem. And this is the first efficient algorithm that achieve an approximation ratio that depends only on K. And also our algorithm is very simple as it is just local search. So one special case of this problem is when K is the minimum of M and N, and we call this the maximal case. And for this special case, then this problem is equivalent to the largest volume simplex problem, which is a very well-studied problem with the best and high approximation ratio of 2 to the O of K given by Nikolov in 2015. And in the same paper, Nikolov proposed the general case as an open problem. So the main motivation in studying the general case is to get a determinant, to approximate the determinant lower bound of hereditary discrepancy. Specifically, we want to get a constant approximation of the determinant lower bound and an log n approximation for the hereditary discrepancy. So these 2 quantities are very important quantity in discrepancy theory. I will just given the formula here. So I should know that like Nikolov, Tangwa, and Matusek already have some polylog approximation of hereditary discrepancy and the determinant lower bound, but they cannot achieve the approximation, the best approximation ratio of O1 and O log n here using their technique. So our work is sort of first step in trying to achieve this goal that we fail to achieve a constant approximation of the determinant lower bound. So the main technical difficulty for local search in this situation is that usually with local search, you start from some set and then you exchange one element from that set to another element outside and try to improve the objective function. Here, this strategy would fail for our problem. For example, when you consider the diagonal matrix here, then if you only exchange one row or column, then you will stuck with a matrix with like which is very bad approximation. So in order to move to get a good approximation, you need at least to exchange both rows and column per iteration. So you need to exchange you need at least 2 exchanges. So our algorithm is very simple, and the idea is exactly this type of 2 exchange operation. So each step you exchange either a row and a column, or at most 2 rows and no column, or at most 2 columns and no rows, and try to improve your objective function. So the main technical part of our work is to analyze the approximation ratio. We had an approximation ratio of k to the O of k. And in order to get this approximation ratio, we introduce a new an analog of the classical plug correlation. So classical plug correlation is an algebraic expression among maximal minors of a matrix. The 2-dimensional is also a similar algebraic expression, but the terms, the rule of like the term being included change a little bit. So it's easiest for you to look at this picture. So in the classical case, so each term here is a product of the submatrix of the determinant of the submatrix in red and in blue. So he said that like the product of the determinant of the red and the blue submatrix can be rewritten at the thing on the right hand side. And the 2-dimensional case is also similar, but here instead of exchanging only a column, you are exchanging both rows and columns here. So this plug correlation could imply an approximate 2 exchange axiom that can be seen here. So it's an inequality among the product of determinant of k by k submatrix of A. And these 2 lemma will be the main technical contribution of our work, and I think they could be potentially useful for other application outside of this subdeterminant maximization problem. Yeah, so some open problem. So as I said, we failed to get an O1 approximation for the determinant lower bound, and notice that like these local search can only get a k to the O of k approximation. So our analysis is tight for local search. So yeah, and that's a more technical open problem, which I can explain if someone is interested. But I think that's the end of my talk, and thank you for listening. And I will take any question.
Let's thank June. Any questions? All right. If not, let's thank all the speakers, and that's the end of the session 3, and I think that's the last session for today. So just wanted to remind everyone that there is longer versions of these talks are there on the YouTube channel, and there are links to this from the schedule and there's a random session after this.
Thank you very much.
Thank you.
Thank you.